Hey everyone, in this AP Chem series video, we're going to go over Coulomb's law and talk about what it has to do with chemistry. To do this, we've got to remember some things about nuclear charge, in particular, the two ways to describe the positive charges at work inside an atom. Take this oxygen atom, for example. It has a nuclear charge that is the result of the protons in the nucleus. 8 protons on oxygen means a nuclear charge of +8. We've also got the effective nuclear charge, which takes those 8 protons into account, but also considers the core electrons that cancel out or shield some of that +8 charge from the protons. Here, this oxygen atom has 2 shielding electrons, leaving us with an effective nuclear charge of only +6. In this video, we're going to look at what nuclear charge tells you about an atom and its properties. So Coulomb's law is the official name for something we've all heard of. It's the idea that similar charges repel each other while opposite charges attract. In the chemistry world, it's the reason that an atom is held together in the first place. The negative electrons are attracted to the positive nucleus, while at the same time the negative electrons are repelling away from each other because they have the same charge. Diving a little bit deeper into Coulomb's law, we'll find that the strength of this attraction actually depends on 2 different factors. One is the charge magnitudes and the other is the distance between the charges. Let's focus just on the charge magnitude part of this and see how it works by comparing a carbon atom to a nitrogen atom. In both atoms, there's an attraction between the electrons and the positive nucleus. In carbon, however, the nuclear charge is +6, whereas in nitrogen, it's a +7. So we can see that nitrogen's nucleus is more positive. The Coulomb's law way to describe that is by saying nitrogen's nucleus has a greater charge magnitude. Why does this matter? Well, it means the attraction between the electrons and that nucleus will be stronger. For carbon with a lower charge magnitude, the attraction will be weaker. This is a super important idea. Let's summarize it by saying that a greater charge magnitude results in a stronger attraction. Let's switch now to the second factor, the distance between the charges. In my nitrogen atom, both of these electrons will be attracted to the nucleus, but the strength of that attraction is not necessarily the same. As you might guess, the electron that's closer to the nucleus in the first energy level will have the stronger attraction to it, while the one that's farther away will have the weaker attraction. And that's another super important idea. Let's summarize it by saying a shorter distance results in a stronger attraction. These are also the key ideas for this video. Make sure that you've written them down. So let's close the video with an example where we compare the attraction of the valence outermost electrons to the nucleus in sodium, magnesium, and beryllium atoms. Let's first get a look at where those valence electrons are by writing configurations for sodium, magnesium, and beryllium. Next, we can start to analyze the attraction based on these 2 factors, distance and charge magnitude. Let's start with the distance factor, and to do this, I like to draw in a little visual aid to help see where the nucleus might be relative to the first, second, and third energy level. So I'm going to draw a little positive nucleus to the left of each configuration and label it with the nuclear charge. Sodium has 11 protons, so a nuclear charge of +11. Here's magnesium's +12 nucleus, and beryllium with a +4. So the configuration itself gives me a pretty nice visual for distance. What I mean by that is beryllium's valence electrons that I'm underlining in red are in the second energy level. So I can see just based on how it looks that the valence electrons in beryllium are closer to the nucleus. That's compared to sodium and magnesium's valence electrons, both in the third energy level, and they're going to be further away. That shorter distance in the beryllium atom is going to suggest a stronger attraction between its valence electrons and the nucleus. Now we have to look at this other factor, which is the charge magnitude, and see what that tells me about the attraction. Starting with sodium, I can see its nucleus has a +11 charge, but it also has all these inner shielding electrons that are canceling out some of that positive charge. That means the effective nuclear charge that these valence electrons are being attracted to is the +11 from the nucleus, but subtracting out 10 from these 10 inner shielding electrons, meaning the sodium atom has an effective nuclear charge of only +1. The magnesium atom has a +12 nuclear charge with the same 10 shielding electrons. Subtracting them out gives me an effective nuclear charge of +2 in magnesium. And in beryllium, we've got a +4 nucleus with only 2 shielding electrons. Subtracting those out gives me an effective nuclear charge of +2. And now I can see that magnesium and beryllium both have greater charge magnitudes, suggesting a stronger attraction. All of this information tells me that sodium's valence electrons will have the weakest attraction to the nucleus. Not only are they farther away, they also experience the smallest effective nuclear charge, or the lowest charge magnitude. At the same time, I can say that beryllium's valence electrons will have the strongest attraction to the nucleus because they are closer to it and have a greater effective nuclear charge, or a greater charge magnitude. And that wraps it up for this video on Coulomb's law. Thanks for watching, and here's a brief summary.